So hello guys, my name is Amit. So today we are going to solve this problem, lead code problem number 100, same tree. So the problem is, if we have two trees, we are given two trees, two root nodes, and we need to find that both the trees are same or not. For example, these trees are same, so we have to return true in this case. These trees are different, so we have to return false in this case. Even these trees are not same because the left of root node is 2 and left of root node is 1, so we have to return false in this case. um, and we have to write a function to check trees are same or not. uh, Two binary trees are considered same if they are structurally identical, nodes have same values. Okay, so how we are going to approach it? Let me open a notepad. Okay, so there are two approaches to it. What I think, there might be more. So first approach is taking a vector. Um, so what we can do is we can do an in-order traversal for this node, for this tree, and store it in a vector. So if we do in-order traversal uh, of the first tree, it will be something as root, um, then it will be as left, and then right. And for the second tree, it will be again 1, 2, and 3, and then we can compare both the vectors. But this approach will have the space complexity, which is equal to um, the number of nodes in a tree. So it will be on, rather 2on, but we can say it on. So the second approach, which we are going to take here, is that we are not going to take the vector. We are going to compare uh, the nodes or elements of the tree, and we'll um, traverse both trees in same order, right? Traverse both trees. So for example, we'll start from 1. If both nodes are same, we'll go to left. If both nodes are same, we'll go to right, and so on, right? So here we'll start from 1, both nodes are same, go on left, but here it is 2 and here it is empty, so we'll return false. So for this approach, we have some uh, so before writing the program, let me see what are the constraints here. So first constraint is, if both root nodes, that is A is equal to um, null. uh, Let us say this is A and this is B, because in question also we are okay, we are saying it as P and Q. Let us say it as A and B. That will be easy. Okay, so if A is null and B is not equal to null, so in that case, or we can say not as constraint, we can say return false conditions, right? So in this case we can return false. Then what other condition, on in what other conditions we are going to return false, uh, and vice versa. That means if B is null and A is not equal to null, it means that either one tree is null and other tree is not null. These are the two conditions. What other conditions can be? So one condition can be something like this. This tree, if we see here, that on one tree the left element exists and on other tree left element doesn't exist. So we can say if A left is equal to null and B left is not equal to null. So in that case, we are also going to return false. And also we are going to think the similar situation for the other. For example, if this doesn't exist and this exists, and similarly for the right. So while writing the code, we are going to see it. And on what condition we are going to return true? Return true condition. So return true condition would be that if we are at the leaf node, for example, we are at node 2 in both the trees, and we do not have anything on left and right. So in that case, we are going to return true, right? So we are on leaf and nothing on like nothing in no child, or we can say, and no child. So in that case, we are going to return true. Um, so it will be something as we can say if A is equal to null and B is equal to null. So in that case, we are going to return true. So with this, let's quickly jump onto our program and try to um, see how we can write the program. So is same. So first of all, as I said, let me check the first condition for returning the false. That is if um, A is equal to null pointer and B is not equal to null pointer, um, or another condition if B is equal to null pointer and A is not equal to null pointer. So uh, not equal to null pointer or taking it as it is, uh, it's the same. So we're going to return false. If both nodes are there, then I can just call my test function. I can just pass A and B and it'll return test function. So what is test? Test is same as it is, but it will be a recursive function. So I think test is pretty easy. So um, fail condition, or maybe we can say return false condition. So as we have seen what the return false condition is, that if A, there exists an element on left of one tree and there doesn't exist an element on the left of other tree. So in that case, we are going to return false. So let me just write that condition. If A um, left is equal to null pointer and B left is not equal to null pointer, one condition. Similarly, I'm going to do it 4 times. Uh, right, let me just, okay. So what other condition would be if A left is null pointer, let us consider this, and B is not this, right? So now this one, if B left is equal to null pointer and A left is not equal to null pointer, and similarly for right, if A right is null pointer and B right is not a null pointer, that is B has some child, and similarly if A, oh sorry, B right is null and A right is not null. It means that B right, that is the right side of B doesn't have any child, but right side of A has a child. So in in all these cases, we are going to return false. That's correct. Um, Otherwise, so what happens in this good case? So in this good case, this doesn't returns false here. It reaches test. So in test, it checks all these conditions are not met. It will go to left. So okay. So for going to left, let me go to left, A left and B left. Okay. Um, then it goes to left and it reaches here. So yeah, again I need to check the values for the return false condition. Um, that if A value is not equal to B value, right? That can also be one condition that trees are structurally same, but value of nodes are not same. So in that case, I have to return false again. So this is also return false condition, right? I think you are following. So I'm at node this one. Both nodes are same. So in that case, I have to return true. So this will become base case if A is equal to null pointer. So what happens is it goes to A left, that is 2's left, which is null pointer, and this 2's left again, which is also a null pointer. So if both are null pointer and B is equal to null pointer, So in that case, we are going to return true. So this is our breaking case maybe, right? And I think we can take it as let ret1 is equal to this one, and let ret2 for the right subtree as well, and we are going to return ret1 and return 2. So let me try running this one. Okay, it says, oh sorry, I was using the Rust syntax. Let, so bool return 1 and return 2. Okay, it passes. So let me try with this one. Mm, okay, it says a val uh, is not equal to b val. So what it says, member access within null pointer undefined behavior. Okay, so it says if a is null and if a val, a is my root, my tree, and this is also my tree. So in that case, what will happen here? So let me think for it. Oh, sorry. So these are not and, these first should be or conditions. Um, A left, B left. Let me try to run it now. Okay, let me try to submit. Okay, so it's faster than 43%. So let me just try to optimize it. Let me not take it um, in here, and let me try to return without taking extra variable. Let me delete this as well. Okay, so it came faster than 100%. So this is the logic. I think that's pretty simple. Just returning false on the conditions on which we do not want to go, and whenever we reach end of both the trees, that is on the leaf node, which do not have any children, we are going to return true. So what will be the time and space complexity for this solution? Let me just try to explain the time and space complexity. So the time complexity would be on, because in both of the trees we are going to every node. That is, if there are n nodes, we are going, if we reach here, we are traversing all the n nodes, and the space complexity would be log n. Why? For example, let me consider we have a bigger tree, something as 1, 2, 3, 4, just bear with me, 5, 6, okay, 7, something like this. So we are here, and we recursively will go to, so both the trees are same. We recursively are going to the node 2. So what happens is a new function stack is created for element 2. And similarly for like one function stack will have pointers to both the tree nodes. Now we have gone to here. So until these three, 1 to 4, we found that all elements are same. Now what happens? We are like we found it same, and we like iterate back or traverse back, or maybe we go back to the node 2. So in that case, what happens is we delete this node, right? And then we go to 5. So at any time, we are traversing to the height of the binary tree. That is the space complexity. At any time, we are only allocating log n stacks for the tree. That is the height of the binary tree. So that's the time and space complexity calculations. So thanks a lot, guys. Have a good day. So this is problem number 100, uh, and this is recursive. Maybe I'll go ahead and do it with iterative in next video. Yeah, thank you. Bye bye.